inviting me here. And after coming here and listening to other talks, I realized that this is probably not the optimal choice of topic. So instead of this, I should have this Monty Python image of a man playing piano with his teeth with the caption, and now for something completely different. And I also noticed that the wiser souls have decided to opt for 1 hour extra sleep instead of coming here. Okay, so that's the outline. Before I start, this is joint work with Aristotle Arapustathis in UT Austin and Suresh Kumar, who's in same institute as me, IIT Bombay. And okay, so that's the outline. So I'll start with the discrete problem, which is classical, and probably many of you know about know all of it. But just to set up the framework, then I'll describe what the relative value iteration for stable diffusions is. Then I give a brief survey of some results from what's called monotone dynamics. That's because I'm going to use those results. And then that's used to prove convergence of the relative value iteration. And there are a couple of extensions. One is to zero-sum games, which is it's sort of routine. But what's interesting is that as a spin-off, you get relative value iteration for risk-sensitive control as well. Under some technical conditions, you can get that. And what's interesting is some kind of offset you have to keep subtracting, and the form it has for risk-sensitive control is not what we expected. It's somewhat different. You'll see that. And then so I mentioned that I was going to talk about relative value iteration for stable diffusion. So there's some kind of a uniform stability assumption. So in the end, I'll just mention recent work where we relax that and instead put a condition on the cost which penalizes instability. Okay, so the motivation is as I said, the classical algorithm for control Markov chain. So let Xn be a control Markov chain on a finite state space, and one can generalize this a bit, but let's stick to finite state space with transition probabilities, controlled transition probabilities Pj given I comma u, which is the probability of going from I to j under control choice u, where I assume that u takes values in some specified compact action space, and Gn is a control process. So Gn is the control chosen at time n, which takes values in u, and then the evolution is described by this. So the probability that at time n plus 1 you are in j given the entire past is p of j given the current state xn and the current control Gn. And I'm interested in the ergodic or average cost control problem, which is to minimize the long run average. Okay, this limit may not exist, so I read lim sup. So this is a well studied problem, and the aim, one generally interested in what's called a optimal stationary Markov control, that is the optimal control which depends only on the present state, and that too in a time independent manner. So the Gn should be some function v of xn, and under suitable conditions you get a characterization through the associated dynamic programming equation, which looks like this. So this cannot be derived by the standard arguments of the one-step analysis, first immediate cost plus the rest, because this is a long run average. Any finite stretch does not matter. So you have to start with the discounted infinite horizon cost and do some renormalization and pass to the vanishing discount. Limited, this is what you get. And the important thing to note here is that there are two quantities which are unknown, this vector v, the value function, and this scalar beta hanging around there. So this is an equation in v comma beta, and if you assume irreducibility under stationary Markov controls, then these are kind of standard results. V is unique up to an additive scalar. So if you look at this equation, it's clear that if you add a scalar constant to v, it changes nothing. So this is the best you can hope. So v is unique only up to an additive scalar. Beta is unique, and it's in fact the optimal cost. And if you minimize the right hand side, you get the optimal stationary Markov control, and vice versa, in this necessary and sufficient condition. So this minimization here gives you u as a function of I. So that let's say u is v of I, and then Gn equal to v of xn is your optimal choice. Okay, so Okay, so what that tells you is that if you have solved this equation, you essentially have solved the problem, because just for each I you minimize the corresponding, do the corresponding minimization, and you know the optimal choice. So the point is to solve this equation, and this is a fixed point equation. So you have v as a function of v and beta, of course, here, and one standard algorithm is what's called relative value iteration. So the oldest reference I know is this DJY. It's slightly different from this, his version, but essentially the same idea. So what you do is just iterate, but instead of beta, I'm plugging in value of Vn. The guess at time n is Vn. The value of Vn at some fixed state I0 is the constant offset I keep subtracting. Because this is unlike, you might have seen the discounted cost, where this kind of iteration Vn plus 1 is some function of Vn is a contraction, and there's an exponential convergence to the fixed point. But here it's not a contraction, and if you don't have this, and say k is positive, then this would simply blow up. So you need to subtract off some offset at all times, and this is one of the choices. And then one knows that Vn will converge to V star, which is the unique solution to the dynamic program, satisfying. So as I said, the DP equation does not have it has a solution that is unique only up to an additive scalar. So if you fix the value at one point, then that renders it unique. So this will converge to the solution corresponding to V star I0 equal to beta, and this, as you expect, will go to beta. Okay. And as I said, this is not the only possible choice. More generally, you can allow for you can replace Vn I0 by f of Vn. It should be Vn here, and satisfying these conditions. So for example, some say average of Vi or min of Vi. If I recall, White used min of Vi, but there are several choices which are possible. Okay, now I want to consider the continuous time analog. Actually, there's no reason to look at it, but it so happens that this arose in a different work on reinforcement learning. So if you write a reinforcement learning algorithm based on relative value iteration, what you end up doing is to write the stochastic approximation counterpart of it. So you replace the conditional average with respect to transition probabilities by an actual evaluation at a sample, and make an incremental move with the standard stochastic approximation step size. And then to analyze that sort of random algorithm, random iteration, the one standard approach is to look at this differential equation limit, and that turns out to be this. And if this converges, then there's a standard theory which will tell you that the algorithm will converge to the same asymptotic limit with probability 1. So it turns out to be this. Now to analyze this equation, so here as you note, I am subtracting xi0 of t. What we did was to consider a related differential equation where you pretend that beta is known and plug that in. So this is the relative value iteration. Let's call this continuous relative value iteration. Let's call this value iteration. This some abuse of terminology, but it's okay. So you plug in beta, and then it's of the form. This is of a simpler form. It's of this form. So it's kind of fixed point seeking differential equation, and you can show that this is non-expansive with respect to the sub-max norm. And then one can show that any such equation actually non-expansive, assuming that the set of fixed points is non-empty, it will converge to the set of fixed points, which in this case is just V star plus arbitrary scalar. Okay, so it's unique only up to additive scalar, so it's a line which is the set of fixed points.
Is existence of uniqueness clear here? It doesn't have to be smooth, it's functional.
Yeah, but it's Lipschitz.
It is?
Yeah. It's a max or finite set of linear functions.
Oh, and you're on a compact set too?
No, it's a finite state space. So.
Oh, okay.
A finite action space. Sorry. Oh, sorry. U. Yeah. Max is over U. Yeah. U is compact.
Right.
Yeah.
Because if U was not compact.
Yeah. Yeah. That's true. So if you look at the differential equation alone, it will tell you that it will go to some Y star depending on the initial condition. But what one can show is, so I mean, this is easier to, this equation is easier to analyze, but the asymptotic behavior is less satisfactory in the sense that it goes to a set to some point which depends on the initial condition and will change with the initial condition. But the original equation is related to this and it has better behavior. What one can show is that yt and xt, if you just by manipulating the two equations, you can show that it differ only by some constant multiple of the constant vector 1. Sorry, scalar multiple of the constant vector 1. So some rt times the constant vector. And you can derive equation for this you show that rt will converge to beta minus y naught star, where y star is this limit, and you put both together, you get xt going to the v star you want. And then you go back to the reinforcement learning algorithm and using standard sort of passage from differential equation to the stochastic approximation, you claim that the reinforcement learning algorithm will converge to v star with probability 1. Okay, so this is the program which we want to carry out for diffusions. That's the ODE aspect, not the reinforcement learning. So that's the question we put to ourselves: is this possible for continuous time and continuous state space problems? And the answer is yes for some classes. So let me now start with the main result. So controlled diffusion is a stochastic differential equation controlled through the drift. So W is a Brownian motion independent of the initial condition. UT is non-anticipative measurable control. Is the most general class one allows. So what that means is that the future increments, so at time t, Wt minus Ws will be independent of U up to time t. Okay, so it doesn't look into future, doesn't anticipate the jumps of Brownian motion. M is the standard technical condition, continuous Lipschitz, etc., and uniform continuity, and sigma is Lipschitz, and this is important, it's uniformly non-degenerate in the sense that if I consider sigma transpose, the smallest eigenvalue is bounded uniformly away from 0, which means noise enters all components evenly, and that has a lot of good effects. And this we were interested as before in the long run average cost or ergodic cost. And once again, you expect that there should be an optimal stationary Markov control of the form zt equal to v of xt. Okay. So once again, the standard approach is dynamic programming. Okay, before I get to that, let me state this important condition. So you associate this operator, which arises naturally out of the Ito formula, for example, with this diffusion, which is script L u of f, which is grad f bracket with the drift, and half trace sigma transpose Hessian of f. So it's basically sigma mi del f by del xi plus half sigma ik sigma jk del square by del xi del xj of f. And that may be a more familiar form. And this is a stability assumption. We assume the existence of a Lyapunov, stochastic Lyapunov function. So by compact, I mean that all sets of the form x such that this script v less than equal to script vx less than equal to c are compact. Okay, so it's a fairly strong stability condition. Okay, let me assume also that the cost does not grow faster than the Lyapunov function, and define the space of functions which don't, continuous functions which don't grow faster than the Lyapunov function, basically C sub script v. Okay, and then one can prove that this is the dynamic programming equation. There exists a unique v star with v star 0 equal to 0. You have to fix some value. It has the same problem as before, that it's you add a scalar, nothing changes, the equation doesn't change. So this is the equation. If you add a constant to v star, it won't change anything because this is a differential operator, it will kill it. So I fix, say, value v star 0 equal to 0. Actually later on I go to v star 0 equal to beta, so perhaps I should have put beta here. And a unique beta satisfying the Hamilton-Jacobi-Bellman equation. Again, beta is the optimal cost, and gt equal to v star xt is optimal if and only if this is v star is the minimizer. So let me fix an optimal control. Okay, so this I should have given a reference to this. This is in the red book, which is there was this red book of Chairman Mao, which is going out of fashion, and it's about to be replaced by a book called Ergodic Control of Diffusion Process, in popularity by Arapostasis, Borkar and Ghosh.
Is it the one that's called the Red Peril?
Not yet. Don't start rumors. Okay, so the relative value iteration, of course, then is the, just by analogy, you write this parabolic evolution equation. So I am subtracting where beta should have been, I am subtracting the value at 0. And we know, just by analogy with the finite dimensional case, we know that it's better to look at this first and then connect the two, which is what we do. So you plug in beta, call this value iteration. Okay. Okay, so again the same question, does it converge? So we first analyze the simpler equation with the value iteration, and just there's a comment. So there's a similar, this kind of a dual situation which was analyzed by Kosminski. He looked at the forward Kolmogorov equation, the Fokker-Planck equation for probability density, and he established that it converges to the invariant density. So, and he called that the stabilization of Cauchy problem. This has a similar flavor. Okay, so let me have this short tutorial on monotone dynamics. This is of course tweaked to suit our purposes. I mean, this the way it is taken. This is most essentially from this book by Hal Smith, Monotone Dynamical Systems, and he uses a more general framework. And many of you might have seen one case of this, which is the cooperative differential equations, which are used extensively by, I think, Angeli and Sontag analyze monotone control systems, and also a lot of algorithmic applications like Kushner and Whiting. Then I myself have used it in various scenarios to you write, as usual, some stochastic approximation algorithm, go to the ODE limit, and if it is cooperative, then there's a theorem of Hirsch, which is some abstract form of which I will state soon, that tells you that it converges for almost all initial conditions if the trajectories remain bounded. Okay, so it's the same thing essentially, but a more abstract form. So let me take H to be something in the intersection of S and G, where S is a metric space. Actually, I think this perhaps might as well be equal. S is a metric space and G is a Banach space with a positive cone G plus. And this is a semi-flow, which is the usual condition that phi 0 is identity and phi t composed is phi s, phi t plus s for t is non-negative. And so let these less than equal to and double less than equal, or strictly less than equal to, denote orders relative to G plus and its interior. Now you say that the semi-flow is strongly order preserving if you have the initial conditions H prime dominating H, then the flow eventually the corresponding, I think they should have been H and H prime. There's a lot of typos here. Some of them I'm noticing now for the first time, this one for example. Then this from some time onwards the corresponding flows should dominate appropriately. I mean the phi t of H less than equal to phi t of H prime from some t naught onwards, and it's eventually strongly monotone if actually you get the stronger inequality. And as you might expect, the eventual strong monotonicity implies the strongly order preserving property. Yeah. So this eventual strong monotonicity, which is a stronger condition here, implies this, which is the SOP. Okay, let script t denote the set of equilibria, which is phi t h equal to h, the points that do not move under the flow. And then let's define the set of quasi-convergent points as the set of initial conditions for which the dynamics will converge to the set of equilibria, and convergent points as the set of initial conditions for which the dynamics converges to a particular, to some point. It's a point convergence. So this is a convergence to a set. It doesn't have to convert, phi t h doesn't have to converge to a point. And here it's a convergence to a point. So this is a stronger condition than that. Okay, and this the abstract version of Hirsch theorem is this, that if phi is strongly order preserving semi-flow and satisfies some technical conditions that this should be approximating sequences from below and above with this property that the omega limit sets have compact closures. But this is the counterpart. As I said, the famous Hirsch theorem for cooperative differential equations is that if the differential equation is cooperative, that is, if you x dot equal to fx and del I f by del x j for I not equal to j is positive, and the trajectories remain bounded, then it will converge for almost all initial conditions. So this is the counterpart of the trajectories being bounded. So remember, and this has to have a compact closure. The flow has to have a trajectory has to have a compact closure, and then you know that almost all initial conditions are either quasi-convergent or convergent, and this is actually a slightly stronger claim. It says that those which are not are actually in the closure of the convergent conditions, but that's enough for us that almost all initial conditions will converge to the set of equilibria. And if the script E is totally ordered, then in fact these two are identical. So if script E is the set of equilibria is totally ordered, then for almost all initial conditions you converge to the set of equilibria. And in fact, if it is closed as well, I should have stated that, then of course because of this, all initial conditions will converge to the to some equilibrium. Okay, so that's in fact the part we use. We have a situation where you have a ordered set of equilibria and which is closed. Okay, so I just sketched the way you apply it here. So text script H, that's why I started with that odd intersection in the beginning. So this is the convenient space to work with the continuous functions which don't grow faster than the Lyapunov function and twice continuously differential function. And now first you have to of course show that the value iteration is a well-posed partial differential equation. That's not hard. So we just take off-the-shelf results from PDE theory and it works because it's non-degenerate and there's no issue there. Now well-posedness of RVI, that because of this VT0 being subtracted needed one extra step. So you just consider the same parabolic equation which it had minus beta here somewhere on the right hand side. You plug in some minus GT, some fixed function GT say. Then once again you can invoke the standard PDE theory and claim well-posedness, there's a unique solution, etc. for some arbitrary fixed GT replacing V. And then look at this fixed point problem, G going to G equal to V at 0 going to V, and you argue that it is a unique fixed point, and that tells you that the relative value attraction will have is well posed, so it has a unique solution in a suitable class. So this part is not too hard actually. Then boundedness of trajectories follows from an estimate of this kind. This is because of the Lyapunov condition, which is quite strong as I mentioned, but it helps a lot. And compactness of orbit uses, again go to PDE theory, it tells you some nice bounds on the Hölder continuity bounds on the second partial derivatives. So essentially Arzelà-Scauli type of, you can just read the result of PDE texts, but that's what is involved. Once you have derivatives also equicontinuous, then you get compactness of orbits. And ESM and SOP, so this stronger property follows eventual strong monotonicity from this estimate. So again, because of non-degeneracy, it has strictly positive densities at all times. So if this is greater than, in fact this is bigger than this here, so this is strictly positive, and that ensures that this will also remain strictly positive. Now this set we know is just V star plus constant, and so this is a totally ordered set and closed. And oops, where am I? No, sorry, C is closed. Yes, sorry, not E. C has to be closed, and there's a typo here. This should have been V naught prime. So if I start with two different initial conditions, you get a bound like this. This again thanks to the Lyapunov condition, and that implies that the set of convergent points is closed, and all that put together you will get the convergence of the relative value iteration from the convergence theorem for monotone dynamics, of value iteration from convergence theorem for monotone dynamics. Then you compare the relative value iteration and value iteration, and you can show some explicities. You can actually show that it's equal to this quantity which as t tends to infinity goes to beta, so you get V going to V star plus beta.
That's the differential equation minus the difference equation.
Yeah.
Okay.
So it just turns out to be a scalar, basically, just like in the finite dimensional case. Okay, there's another alternative proof which also works, which is to take this psi t comma x as this. This is similar to what we had used in risk sensitive control, if you remember. So plug in, define MT as psi of t comma x star minus t, and this is where this is an optimal process. Under the optimal Markov code will be star, and this ends up being a convergent reverse martingale. So therefore, it has and because the process is positive recurrent, it can converge only if this quantity is constant almost surely, and by continuity it has to be constant everywhere, and then you go back to the rest of the argument is as before, and you fall back on the previous argument. Okay. So I gave some of this work I had presented earlier in one of the applied probability conferences, and Eugene Feinberg asked me what about countable state Markov chains. It hadn't occurred to us that people had not done that. Apparently not. It's quite easy compared to the diffusions, and the same motion units you can go through, and under reasonable assumptions on the rates to ensure that the jumps don't accumulate and so on, the usual ones.
Would it be useful to say what the analog is of the uniform elliptic conditions? So
we put a lot of tame conditions on the rates to prevent any kind of strange behavior. So bounded from below and above and so on, so that. So it goes through quite easily for continuous time Markov chains. Okay, so let me talk about zero-sum games. So now you have two people, UT and VT, the two controls. One person trying to minimize what the other person is trying to maximize. This is the payoff. Now you move over to relaxed controls, which is like mixed strategies. So these are probability major valued controls. And then you have this, you can analyze the corresponding AJI equation, which is this one. And the corresponding relative value iteration would be again what you expect. I mean, just the min got replaced by min max, and the value iteration, if you knew beta, would be this. Okay. Now again, this more or less straightforward extension, and one can show that phi will converge to the appropriate solution of the ergodic case. Okay. And the reason we are interested in is the application to risk sensitive control, which is to minimize limb sup of this log expected value of exponential cost, which is quite popular with finance people, for example. And see the way, so this is a control problem, not a game problem. The way you convert it to a game problem is by using the standard log transformation, which you look at the AJB equation and apply log transform, you get the AJI equation for a stochastic differential game, which is the trick, which is, it has a long history actually. Something called Kohlhoff transformation, which converts Borkar's equation to heat equation. That's probably the first instance, but it has been used extensively by Fleming and collaborators, both for risk sensitive control and large deviations.
What's the second player doing? What's the interpretation?
Yeah, so I'll come to that. So there's when you take the log transformation, it's a AJI equation for a game problem where there's another additional artificial control which has a quadratic cost. So the payoff will end up becoming C x comma u minus half norm u square. Sorry, minus half norm v square. The v is the other guy's control. And if you solve the equation, of course it's quadratic, so you get the optimal v proportional to the gradient of the solution. And because of that, we have imposed this fairly strong condition called asymptotic flatness. We will write down here what it is. So it's conceivable that one can do this more generally, but we just wanted to reduce it to what we already know. So there's this condition called, this is kind of, it's again a Lyapunov condition, but much stronger. And what it ensures is the following. So if you start two processes with two different initial conditions, but with a common control process. So this is common, same control process, same Brownian. So fix the control process U and the Brownian motion, but change only the initial condition. Then they approach each other exponentially in the mean. So this was introduced by Basak and Bhattacharya in their work on ergodicity of diffusions. So what, as you can expect, what it ensures is that if psi is the solution of the AGI equation, then grad psi will be bounded. Because you can, those who are used to stochastic control can see it easily, because if you start with say discounted cost, you can get Lipschitz, uniform Lipschitz condition independent of the discount factor, then passing to the limit you inherit the condition for the ergodic AJB equation. Okay, and because as I said, the cost for the adversary is half norm v square, and you solve the quadratic problem, it ends up being v equal to something times grad psi. This allows you to consider a compact control space. That's where it helps, and it reduces to what we already know. So, okay, so here's some summary of the AJB equation is this. And what's interesting is that, okay, so you convert to the game problem, and then we know what happens, but then you convert it back by inverting the log transformation, and the relative value iteration for the risk sensitive control uses it's a being this. It has this log, you subtract, you don't subtract psi t0, you subtract its logarithm. Somehow we didn't expect, maybe it should have been expected, but we didn't expect it. So this is the offset you have to subtract, and then the convergence follows. So one slide for the no details. This turned out to be amazingly hard. We thought it would be just not a terribly difficult extension, but turned out to be extremely hard. So this is, as I said, we don't assume uniform stability, but it's a condition on cost. The cost kind of energy, like it penalizes instability, and again we have convergence for V naught bounded, and it's only recently concluded the proof of this, thanks largely to the Aristotle Arapostos's expertise of parabolic Harnack inequalities and such.
But the thing is, it's harder with V naught bounded. I mean, if V naught's a Lyapunov function, it's easier.
Yeah, so we had to assume Lyapunov condition for the optimal control, but not uniformly, not under all controls.
But I would say the initialization, convergence is easier with V naught's a Lyapunov function.
We tried that actually, we did not succeed. We tried with initial conditions of the order of capital O of V star, script V. Should be possible, but as of early this week we were struggling with it.
With uniform ellipticity and V not being a Lyapunov function, I think I proved that evaluation converges like that. I'm not sure. And so, and you think the same tricks would work. I don't know.
No, you had what you did for policy iteration.
Policy
Yeah.
paper,
Yeah, no.
I don't know.
No, I mean, because of your paper, we were expecting it would be true here, but seems hard to.
Curious.
So that's essentially it. So the first part has already appeared in SAM Journal of Control and Optimization. Second, we were submitted to this proceedings which periodically appear associated with the symposium on dynamic games. And this one is essentially ready, but yeah, it is what I just said. So stop there.